Good day. My name is Scott Cordella, and I work for the MITRE Corporation, and I'm joined by my colleague, Sam Visner, also of MITRE. And today we are speaking about a topic that we call cyber best practices for space satellites. In this next chart, we show some of the activities that MITRE is involved in with respect to space to give some context for this work. As shown on the left, we show the National Space Council Executive Office of the President and the space policy directives that that group has put forward. Space policy directives 1, 2, 3, 4, and 5. I won't summarize all of them, but rather highlight number 5 in a subsequent chart. On the right, we show MITRE's work. MITRE is a not-for-profit whose business is to operate federally funded research and development centers. MITRE has a uniquely large footprint of operations of FFRDCs. We operate 7 of them, and we work across all of them in favor of large outcomes, such as those that align with these space policy directives. This talk is one of those alignments. It focuses on Space Policy Directive 5, namely cybersecurity principles for space systems. In the next chart, Space Policy Directive 5 has these critical aspects. It seeks to provide protection against unauthorized access to critical space vehicle functions. It seeks to reduce the vulnerabilities of those space vehicles, including their command and control, their telemetry receiver systems. It seeks to protect those systems, communication systems, from jamming and spoofing. Space Policy Directive 5 also addresses issues associated with ground systems of space systems. That is, those aspects that pertain to information technology, information processing systems, operationally dissemination of the information that space systems develop. And explicitly, and to the point of our talk, Space Policy Directive addresses the approaches used by the National Institute of Standards and Technology's Cybersecurity Framework, the NIST Cybersecurity Framework, as the appropriate means to develop these best practices. The best practices that are cited in SPD5 include cybersecurity hygiene practices, physical security practices, machine automation, and others. And ultimately, going upstream of the actual provider of space capabilities, namely through supply chain risks, mitigating those risks. So altogether, these best practices are areas that we will speak about in our paper and relate them to the work that we do through Sam and his team with NIST. First, in this next chart, the space industry threats that we're trying to address, and we can group them in 3 basic groups. One, operationally related threats. As I mentioned, supply chain threats, those threats associated with the integration of new equipment, data, the design of our systems, and so on. A second grouping is business systems, how we manage our space systems, how we provide data security, software assurance, how we train employees, how we manage the overall enterprise of cybersecurity. And finally, the third group is in the missions themselves, how we protect communications to and from the space systems and the ground, how we secure the ground network, how we maintain positive command and control of our space systems so that adversaries cannot do harm. These are the basic areas that we describe as the threats. In the next chart, this is essentially the gist of the talk. What are these best practices? How can we use the NIST cybersecurity framework that's been developed for other use cases, but for space? And address the IT ecosystem that we're trying to develop in support of low Earth orbit, providing greater cybersecurity and resilience. And ultimately, these best practices become guidelines for industry to implement and become more protected through their use. I'll now turn this talk over to my colleague Sam Visner, who can speak in more depth about the NIST cybersecurity framework on the next chart.
Thank you, Scott. And I appreciate very much the honor of being asked to speak at this year's Ascend event. I'm Sam Visner, and I am the director of the National Cybersecurity Federally Funded Research and Development Center. I'm going to talk a little bit about that center in a minute, because that center's approach to cybersecurity architecture is really core to the message that I want to send today. And that is that the security of space systems, particularly proliferated LEO systems, with hundreds and eventually thousands and perhaps tens of thousands of small satellites, is going to be a major challenge. These satellites are designed, as are all space systems, with space power and weight constraints, and more so in the case of these small LEOsats and small satellites than has been the case, for example, perhaps with larger national security and national platforms. So the question is there a way, is there a roadmap to improving the cybersecurity of these systems, particularly these commercial systems, that is incremental? And the approach that I want to discuss today is essentially an approach that uses architecture. And I'm going to point to an example in an industry not necessarily related to space systems, but I think of as indicative and hopefully informative of the approach that one might take. The overarching approach we use to cybersecurity architecture is NIST's cybersecurity framework, which essentially allows for both a self-assessment and the building of a cybersecurity architecture and program according to various phases. Identify threats and vulnerabilities, to protect yourself against these threats and vulnerabilities, to detect threats, to respond to them, and to recover. And these 5 categories allow for the development and the imposition of specific controls which are easy to understand, and the building of a cybersecurity architecture that can be mapped to these phases and to the subphases and controls under them. Let me move to the next slide. What we do in support of NIST is really quite unique. We work with NIST National Cybersecurity Center of Excellence. That center assembles experts from business, from the nation's business infrastructure and community, from academia, and from the government. And we operate in the development of cybersecurity architectures that use essentially commercial technologies that can be employed together to protect the nation's business infrastructure. The NCCOE that we operate is a collaborative environment. And that collaborative environment, as you can see on the next slide, public-private partnerships, we bring in standards organizations from NIST, companies that make cybersecurity products. We look at policies, in this case, like SPD 5, the Space Policy Directive 5, to which Dr. Cordella referred a minute ago. We bring in academic experts, and we bring in experts from the industries that need cybersecurity. So both the product vendors who produce the solutions and those that need them in the various industry sectors. On the next slide, it gives you a sense of how we work. Everything has to be standards-based. We ask, what are the cybersecurity standards relevant to this industry? Everything has to be modular, plug and play. You don't have to use a product that we've used in a reference architecture, but it should allow you to achieve the same functionality and achieve the same standard. Everything is published as a repeatable sort of practice guide on how to do it so that you can, as we say, do this at home. All of the products with which we work are commercially available. There are no architectures that have a big thing in them that says, here goes the super classified technology you can't afford and to which you don't have access. Everything is available. Things have to be usable and practical, and all of the work is open and transparent and published so that the industry, an industry that doesn't have lots of people with security clearances, can use it. Moving to the next slide, the way in which an architecture is published is really quite straightforward. NIST publishes them under the Special Publications 1800 series, known as practice guides. But these practice guides are how to assemble a cybersecurity architecture. Volume A, the problem we're trying to solve and why you want to solve it and what benefits you get from doing so. Volume B, the architecture itself, mapped to the various controls and standards applicable to the industry. And volume C is the assembly manual, right down to the glue code to make different pieces of commercial cybersecurity technology work together. Let me give you an example of how this has been done for the medical industry, in this case for wireless infusion pumps. These are IoT, Internet of Things devices. They're connected to human beings, but they're also connected to the hospital IT. They're connected to the pharmacy. They're connected to the patient's record. They're connected to all of the various IT systems that need to be involved in caring for a patient. These systems were designed initially without a lot of security features. They're connected to the hospital IT estate by Wi-Fi, possibly using a Wi-Fi password. The question was asked, would it be possible to develop an architecture with compensating controls that would add security in the absence of security features on these devices themselves? And this is an architecture that we used. In this case, a fairly complex system with data transfer, physical connectivity, lots of information flow. And in this case, you can even see a wireless link where the medical device was connected to the hospital's wireless network using Wi-Fi. This is the kind of approach that we use, is to specify compensating security controls and commercial cybersecurity products. Going to the next slide gives you a sense. You can see on the left several of the various phases of the NIST cybersecurity framework. In this case, identify, protect, and detect. And within those functional areas, specific categories, and within those specific controls that are applied. And this shows you that the architecture itself maps specifically to the requirements that are requisite to that industry, in this case, the healthcare industry, in this case, IEC, ISO, and HIPAA privacy rules, as well as the specific phases of the NIST cybersecurity framework. In other words, this is an architectural approach that allows us to build an architecture specific to an industry that maps to known controls and a known architectural framework. So moving to the next slide, we believe it is possible to develop cybersecurity reference architectures for all of the segments to which Dr. Cordella referred a few minutes ago. Certainly the user segment, those that in fact represent the workload that'll be carried by these satellites, the space segment itself on board these satellites, as well as the ground segment, with an understanding that more and more of these will be connected through the internet and in future connected through the next generation of the internet, known as 5G. Here's a brief comparison of how these two architectures would work. In the case of healthcare, you can see this delivers medical fluid in a controllable way to a patient using wired and wired networking. A lot of the devices are used simultaneously. Every pump has to be hooked to a server for configuration setup, for updating and drug library installation. There's a small device which on each pump provides a little bit of limited computing. Devices communicate through several different operating systems, which may be fully equipped, or depending on the need, these may be very small and compact operating systems. They're designed for long lifespan usage. Hospitals can't be switching these things out all the time. And they have a complex set of security controls, asset and tracking, inventory management, patch management, network segmentation. We have to be able to look at abnormal behavior and to be able to detect that. Whitelisting, the ability to communicate with encryption, a number of security controls. This has an analog in the space case. If you take a look at this, we have to obtain observations, maybe imagery, or provide communications. So there is an analogous function. Just as we have a large number of infusion pumps, we have a large number of these satellites which are used simultaneously. Every one has to be managed, has to be connected to some kind of a data server for configuration, software update. Just as the medical devices have onboard computers, so do the satellite with limited computing in some cases to be able to manage the functions for which they're responsible. These systems may be designed for relatively short lifespan. That is a difference that would have to be accounted for so that they can be deorbited and replenished, but some of these may stay up for a very long time. And lastly, just like in the healthcare case, a very wide variety of security controls, authenticated communication, the need to encrypt data in transit, access control to the operating systems, whitelisting of the applications that are allowed to be used on these, and the ability to verify input and to constrain input according to that whitelist, to log and audit events, to be able to update devices securely, to make sure that the engineering processes themselves are secure, make sure that antivirus defenses have been mounted and are maintained, to make sure that the BIOSes in the operating systems are secure, and to make sure that they're fail-safe. A different set of controls than in the healthcare case, but like the healthcare case, a wide set of controls. And I believe an architectural approach, the one that uses, for example, the NIST cybersecurity framework, is the way to go. We've used this approach for a number of industries: healthcare, energy, transportation, finance, and others. We think the healthcare approach is a rough analogy. It's not a perfect analogy, but it might be a guide to the approach to building cybersecurity architectures for space systems. SPD5 is a driver. It's a driving event. It makes clear these controls are important. We need an architectural approach that allows us to tailor the controls and requirements in SPD5 to the commercial space environment. With that, we're going to conclude. Dr. Cordella and I are both grateful for the opportunity to have presented to you at Ascend, and our contact information is on the last slide. We would be grateful if you would contact us, and certainly we'd be willing to try to work with you in answering your questions about this approach to securing the ever expanding environment of commercial and small satellite systems. Thank you.